when we apply time reversal operator on a, let's say, spin up state in the z direction, then that turns the state into spin down with a possible phase factor, call it eta here. So this one here. And if we apply time reversal operator on a spin down, then it turns it into spin up state, but with a minus sign. It's a minus sign. So this result, of course, is also true for any spin state. And so if we, for example, have spin up state in a certain direction, n, then this will also be equal to some phase factor times the state in the opposite direction minus, yes. And we apply this to spin down, then it becomes, we have a minus sign. Plus. So I think this is clear. You can also verify this directly by doing this rotation from the spin up state in the z direction to this spin up state along the direction n. Or you can just say that we have a spin up state like this, thing on the n plus, let's say, like we did for the z direction. So the spin operator anti-commute, so that becomes yes, and plus. So then this becomes minus h1.2 and plus, because this is an eigenstate of the Sn. So that's the spin operator along the n direction. So then the same argument follows like before. Yes, that's what it's kind of clear, I think. So there is interesting consequences of this. So let's see. We apply the same operator twice. So if we consider an arbitrary spin state, spin half states, so which can always be written as linear combination of up and down, like that. So if we apply this twice, so we look at it like that. This is an exercise, that's a good exercise. For seeing the effect of time reversal on spin half states. So we have to be careful there because the time reversal operator changes the complex C plus to C dagger, C star. Yes. So we have products like this, and then we get the phase factor, and the spin up state is now turning to spin down. And for the other term is, the other term should be negative then, because it is spin down, so that will turn it into spin up, and the complex number C minus becomes C minus complex conjugate. And then we also have eta, like this. So now we apply this again. So now it is a spin down, so then it becomes minus spin up. So it becomes minus, and the C plus star becomes just C plus, and we get star, because this is eta is a complex number, so everything becomes a complex conjugate, and theta acting on spin down becomes minus spin up with the eta. like that. And the same here, we get then minus C minus E star down like this. But these are just one. These are just one. So then this becomes minus the original state. Yeah, so this is an arbitrary spin state. So if we apply an arbitrary, if we apply the time reversal operator twice on an arbitrary spin state, then we get negative of that spin state. So that means that for spin half states, then we can say that eta squared is equal to -1. For integer spin, we have already worked this out before. For integer spin term, eta squared is equal to 1. So in general, we can think of the time reversal operator when it acts on the angular momentum state as the rotation operator around the y-axis by angle pi. Yes. So we can think of this time reversal operator is some phase vector as rotation operator around the y-axis by angle pi. Yes, because as we have seen that we have seen this for the spin half case. So this is actually true in general because we basically reverse the direction of the momentum. So in this case, we reverse the direction of the momentum along the z direction because it is an eigenstate along the z direction. So we reverse the direction of the spin. So then we can show from this that if we apply time reversal operator twice on the angular momentum state, then the result becomes J. So the sign here is given by this factor here. So for j equal to 1/2, then becomes -1. If j is an integer, then it's just +1. And we can verify this by simply applying, by using this definition here, like we have in the notes. Yes, it's just a matter of inserting a complete set of angular momentum states along the y direction. Then one can show that this result is true. And we have shown this also explicitly for this spin half in the integer spin. But this is also true for any half integer spin. So it could be 3/2 or 5/2 and so on. So then you get the minus sign for those integer halves spin. Okay. There is one important consequence of time reversals. There is a famous theorem due to Cramer's. I think it is called Cramer's degeneracy. So this is a consequence of time reversal symmetry. So if we have a Hamiltonian that has this time reversal symmetry, then the theorem tells us that if we have a system consisting of an odd number of spin-half particles. So for example, electrons, which are often the case we have. Under some external field, so we don't care, this external field can be any field. Then each energy level of the composite system must be at least twofold degenerate. So the theorem only applies to odd number of spin-half particles. Of spin-half particles. So for example, electrons. So how do we see this? Well, if we have an odd number of spin-half particles, then the total angular momentum must be half integer, because this number is odd and the spin is half. So then if we think about adding to angular momentum, let's say G1 and G2, if it is odd, then the total momentum must be also half integers. So let's show that how this theorem is proven. So we start by saying that since the Hamiltonian is invariant under time reversal, then it commutes with time reversal operator. So now let's say that we have an eigenstate of Hamiltonian, so that with eigenvalue En. So then we know that because of this commutation, then we also have theta n is also an eigenstate. Is also an eigenstate. Okay, like this. So let's assume now that this state here, so we assume is non-degenerate, and we want to show that that cannot be the case. Assume degenerate. So we do the proof by contradiction. Assume it's degenerate, then it would imply that this state here must be the same state as the original state, except that we might multiply by some phase factor, call it eta. Yeah. So now if I apply this in time reversal operator twice on the state n, so then that becomes so now we have to be careful again that the time reversal operator. So let's do this step by step. So this becomes like this, and that becomes star. So that becomes n like that. But this is equal to eta times n. So then this becomes just state n, because these are just a phase factor. So it's equal to 1. Yeah. But we know from the previous result that if the system is a half spin integer, then this should be equal to -1, or spin half, or integer half, or half integer spin. Yes, half integer spin. I think that's the right name. So it should be -1, but it's +1 here, so that contradicts the assumption. So this implies that there should be some degeneracy. So the is good. simple there. So let's consider some examples. The simplest example would be to just have one, let's say, electron or one spin-half particle. So we have a state here, like this here, and it's we have one electron, it's spin up. Then the time reverse state, which is a spin down. So we apply is on a spin up, that will give us minus the spin down. So that spin down state is then the degenerate to the spin up state here. Yes. So this is just the Pauli principle that you can occupy the same state by two, let's say, electrons, one up and one down. So these two states are degenerate. That's one example. And we have three. We have a situation like this. We need two levels. Then again, it is also degenerate. Yes, these two levels, obviously. And so on. So we can have more levels, if you like. And the point is that there is always one level which is only occupied by one particle in the case of odd number. Yes. So then there is always this degeneracy. So the Cramer's theorem only applies to odd number of electrons. So it doesn't say anything about an even number of electrons. So that's important to note. And then make no statement. So in the case of an even number of particles, spin-half particles, the state can be degenerate or non-degenerate, depending on what kind of configurations you have. So for example, if I have just two particles, then like this, just one state, then this is, that's the only possible state. So it's non-degenerate. Yes. It's non-degenerate. But I could have a situation where we have, let's say, two, like this, or three, maybe. Then I can have a situation like this, yes, which is degenerate then, let's say like that, this kind of states. If one of the level is only half filled, only one particle occupying the level, then I can have another electron of opposite spin occupying the same level. So we can have degenerate even if we have the number of particles is even. So the theorem doesn't say anything about even number. So that's the point. Now Cramer's degeneracy is lifted, that is to say broken, when we apply a magnetic field. If we have a magnetic field, then there will be a term in the Hamiltonian of this form, S dot B. So provided the magnetic field is external, so the B here is external, so it's not part of the system, then this term in the Hamiltonian does not commute anymore with time reversal operator. That's because the time reversal operator anticommutes. Yes. So this is 0. So that means that if we do this similarity transformation, we get a minus sign. So it doesn't commute. So then the symmetry is broken. So then the degeneracy is lifted. Okay, so that's Cramer's degeneracy. It's an important theorem that has a lot of use in the physics, in atomic physics and condensed matter physics, when you have electrons with an odd number of electrons. So, so now we want to start a new topic. This is time-dependent perturbation theory. So early on in the course, we talked about quantum dynamics, but there we have just a Hamiltonian which is independent of time. And we considered how an arbitrary state evolves under this Hamiltonian. But the Hamiltonian itself is static. So now we would like to consider the case where the Hamiltonian itself is time dependent. So we have, in addition to the static, so this is static, we have an additional potential which depends on time. So we want to consider what to do when we have such a system. And the assumption here is that we know the solutions to the unperturbed systems. We know the eigenfunctions and eigenvalues of the H0, the unperturbed, the static unperturbed Hamiltonian. So we do the exact formulation first, and then later we do time-dependent perturbation theory. So this is one of the main goals here is we want to figure out how an initial state evolves under this time-dependent Hamiltonian. Now, without time-dependent potentials, we already know this. This just involves according to this one here. So this we have already talked about earlier. Yeah. So let's skip that one. Here. Okay. So when we have time-dependent potential, it is usually useful to work in what is called the interaction picture. It's kind of convenient to work in this interaction picture, or sometimes called the Dirac picture, because it was introduced, I think, by Dirac. And we'll see why this is the case. And this is particularly useful when we want to do perturbation theory. So what we find is that we work in this picture, this interaction picture, then the time-dependent Schrödinger equation retains the same form, but instead of the Hamiltonian of the full system, we just have the perturbing field appearing in the Schrödinger, time-dependent Schrödinger equation in this interaction picture. So let's start with a definition of the interaction picture. So it's defined here. So this is a unitary transformation. So we have a unitary operator. So this is if there is no perturbing potential, then this is just like the Heisenberg picture. Yes, because it rewinds the state back to time t equal to 0. So remember, we see that the sign here is positive, so that rewinds the state back to time t equal to 0 if there is no perturbing field. But this is, of course, not the same as the state at t equal to 0 because we have an additional potential which depends on time. So this is the definition. Yes. And the corresponding operator then is transformed in this way here. And this is obtained by using the fact that expectation values of observables should be independent of the picture. And this is a simple way of working out the connection between the different pictures. Yes, just you have to keep in mind that the observables should be independent. So that is what we get here. Yes. So that is just basically saying that if I have state in the interaction picture and I have the operator, then also have to be in the interaction picture. Then they should be the same as the state in the Schrodinger picture. And that gives me this equation here. Yes, I think that's similar as we did for the Heisenberg picture. So in the case of the interaction picture, both the states and the operators are dependent on time. So in the Heisenberg picture, we transfer the time dependence from the states to the operator, and the states then become static. But here, both the states and the operators depend on time. So that appears like things become more complicated. But the gain from this is that we kind of separate out the perturbing potentials from the full Hamiltonian. That makes it easy to perform perturbation expansion. So let's work out then the Schrodinger equation in this interaction picture. So we start just from the definition. And take the time derivative of the state in the interaction picture. And we want to know what is the equation of motion of this state. So we just use the definition of the interaction state that then brings down the Hamiltonian, and we keep the exponential here. Yeah, so that brings down the Hamiltonian. So we have two terms, one from the exponential and one from the state itself. We get 1 ddt. Okay, like this. So the position of this operator can be here after the exponential or before. It doesn't matter because it commutes with this exponential. So now we used the fact that the Schrodinger state satisfies the time-dependent Schrodinger equation, so that is equal to this. So we see then the H0 disappears, so that one and that one disappears. So we get exponential. And then I have the VT. Like this. And then I will insert a unit operator. This is the usual trick. You insert a unit operator. In between the potential operator V and the states. Sorry. So these are just one plus So now we can use the definition of the interaction picture. That is the operator in the interaction picture. So I put label I, and this one here is the definition of the interaction state. So it's nicely gives us this Schrödinger equation in the of the interaction picture. Yes, so that's the corresponding time-dependent Schrödinger equation in the interaction picture. So the nice thing about this equation, as we mentioned before, at the beginning, is that the H0 disappears from this equation. Well, it doesn't disappear. I mean, it's contained in this state here. That contains, of course, the H0. But the equation itself has no explicit dependence on H0. So this makes it convenient to develop a perturbation expansion. So convenient for developing perturbation expansion in V, of course. And we can do the same for the operator. So that let me just write out the result here. It's just quite straightforward, I think. So we have an operator in the interaction picture. Then the equation of motion is kind of similar to the Heisenberg equation of motion, except that instead of the full Hamiltonian, we have the H0. That is the corresponding equation of motion for the operators in the interaction picture. So one thing we should keep in mind is the convention. So the convention is that all states, I mean, like, so maybe I shouldn't say all states here, but rather states in all pictures. At t equal to 0, I'll say. So that's our kind of reference point. T equal to 0, all the states are the same. That's by definition. So you need a reference point, otherwise you can't tell the difference between the different pictures. So we now try to work out the time development of the states. So everything now is exact. There is no approximation so far. It is. So we can always expand a state in the eigenstates of H0. So we have Cn, T here, and like that. So we put the dependence on time in the coefficients because the states n are time independent. We just a reminder that this is equal to. Yeah, so that forms a complete states describe the Hilbert space of the problem. So if we multiply by both sides by minus exponential minus I H0t divided by H So let's do this. And like that. Then this is just showing a state by definition. And this gives me, so n is an eigenstate of h0. So then this becomes cnt exponential minus I h bar en t n, like this. So that's the general form of the time-dependent state. So the task is then to figure out this time-dependent coefficients. So we can do this by using the time-dependent equation. In the interaction picture. So, and then we insert this expansion. So we want to figure out this coefficient. That's the goal. Is somewhere. See. So I have to insert sum over states. States, call it M now, and that is independent of time. So we can put it to the left of the derivative respect to time. Yes. So we do the same on the right hand side. And then the coefficient t. So now we can pick up one of the coefficients on the left hand side by projecting to one of the eigenstates. So let's call it n, like this. So then that gives me d dt cnt. So that gives me t. So this is the operator in the interaction picture. So we want to go back to the Schrödinger picture. So that is equal to h bar 0 h0 t, and then vt to the minus bar 0 t. So this state m and n are eigenstates of h0, so we can replace the operator with the eigenvalues. So we get then sum over m, and then we have the matrix element of the potential in state n and m t, and then we have the exponential, which is I call it omega and m, like that. T, and this omega and m is just the energy difference. So each bar omega and m is just the energy difference between En and Em. So this is it. So this is the equation that determines the coefficients, time-dependent coefficients. So if we can solve this, then we know how the state evolves in time under the presence of the time-dependent field. So this is the first order differential equation for the coefficients. This is of course very difficult to solve when we have lots of states or we have lots of particles. So here we are only talking about one particle with many states here. So if we have lots of states, then obviously these equations are not easy to solve. So you can also think of it as a vector equation or a matrix equation. Think of this as a vector C, so I call it, I don't know, let's call it C, like that. And then right hand side, and then just some matrix multiplication between the matrix V and the vector C. So we can also write it like that. It's just the same thing as this one. Okay, so let's I don't have the time maybe, but we can start. Just continue after the break. So what I want to do now is to apply this formula. So this is an exact formula. This is not time-dependent perturbation theory. It's an exact formulation here. And that's always the case. So usually the case in physics, especially here, quantum mechanics, exact solution is usually not particularly useful because in practice it means you cannot solve it in practice. So, unless the system is simple. So what, and this is the whole point about approximate methods, like time-dependent perturbation theory, is that it allows us to solve problems which are complex but manageable. So we can do this in practical way. We can solve the problems. So, I mean, we know the exact solution, just the Schrödinger equations, but it's not particularly useful when we want to apply it to some real systems. However, there are some problems, simple problems, which can be solved exactly, and they kind of provide a useful model for real problems. And the problem we want to consider is a two-level problem. Let's write it down here. So we have two-level problem like this with energy E1 and E2. And we want to, so we have here. So let me just write it down in terms of matrix now, because we just have two-level. So the Hamiltonian is then just a 2 by 2. And then we apply a perturbing field. And it is in the form of harmonic perturbation. It's called strength gamma. And it has the following general form. Like this. So the diagonal components are 0, because if it is something, we can always, as long as it does not depend on time, so we can always put it in the H0. Yes. So we need to only consider the off-diagonal elements here. So this potential, because of this off-diagonal elements, it will couple the states. So the states will be coupled. by this potential. Yeah. So this problem can be solved exactly, and we will do this maybe after the break. It's a very useful problem because quite a lot of systems can be mapped to this two-level problem. Yeah. So if you have some complicated problems, it is usually well, it's a kind of general procedure that you try to identify the important degrees of freedoms, the important states in the system that are relevant for the physics that you want to study. So very often there are only two states, and then you can do this mapping. You can model the system by just a two-level system, and then you can solve it exactly. Okay, so maybe can have a break here, and we continue with this two-level problem after the break. So let's say a quote after. Are there any questions about this? No? Yeah, everything is clear. Yeah. Okay, then we see in 15 minutes or so. Okay, so let's continue with this two-level problem. So we want to solve this exactly. So we have this perturbing field. So this is of course Hermitian, because we can see that we take the matrix elements to 1. So that is just the same as 1 to complex conjugate. So that means that it's Hermitian. So let's illustrate this by some real example. So one famous example is this spin magnetic resonance. Magnetic resonance. So just to illustrate why we have this type of Hamiltonian. So here we have an electron with some magnetic moment, which is given by E divided by mc times spin, like that. So one places this magnetic moment in some time-dependent magnetic field. So we have a time-dependent magnetic field, which is of the form B0 along the z direction. So that's a static field along the z directions. And then we have a rotating field, that's a strength B1 on the xy plane. So we have omega t x like this, and then minus sine omega t along the y. So you can see here that this is just a rotating field on the xy plane. So it's a harmonically rotating field. So if we write down Hamiltonian, so that is just a minus u dot b. So if we work this up, we find that this is equal to omega z, so operator now, plus omega 1. So we have to define what is omega 0 and omega 1 later. X minus sine omega t and sy like that. Okay, so this omega 0 is just some constant. So let me write it down here, maybe. Omega 1 is just same one, except that we have B1. So now if we use the Pauli matrices for the S operators here, then we get exactly the same form as we have here. So let's see, let me write it down. So that becomes a minus 1/2 h power omega 0 minus 1, like that. And we have for the, so I should have an operator here as a matrix. So this is a function of time now. So that is equal to 1/2 1 0 0 and t. Yes. So we see that we make a comparison between this one here and this one. We see that these are just our gamma, and E1 then is equal to minus 1/2 h bar omega 0, and E2 is equal to plus 1/2 h bar omega 0. So that's a concrete example of this Hamiltonian. Okay, so now let's start to solve this. So we use our differential equations, the first order differential equations that we worked out before. So we have then, we look at the first coefficient, then it will be C1. So the C1 of course depends on time, but I just dropped the time dependence here. So it's cleaner to write. And then I have, let me see, what do I have here? Yeah, so I have the potential in 1 and 2, because the diagonal components is 0, so we only have 1 and 2, which couples to the second coefficient, T, C2. So that is equal to gamma. If we plug in the value of this coefficient, then we get e to the I omega minus omega 0 dc2, I think. Okay, so then we have also the second coefficient. So I want to do this in some detail, as it's an important problem. Then we have its first order differential equations. That becomes minus now C1. So these are two first order differential equations coupled. So it's a set of coupled differential equations of first order. We can then eliminate one of the coefficients to get the second order differential equation. So we eliminate, like I have in the notes here, so let me follow the notes to so otherwise get confused. So I will eliminate the C1. So we just plug the C1 here. Then we get second order in the 2, C2. So we replace C2 here. That then becomes, let me just write down the answer here. I think it is quite straightforward. There, like that. And then we have some coefficients here. So let me just call it C1 like that. C2dt. So I don't want to spend too much time doing this algebra. I think it is quite straightforward. And then we have another coefficient. So let me call it E2 and C2, that of this form. Yes. So if we work this out, then we get the second order differential equation for C2. So let's write that down. So that becomes and then we have t plus gamma upon each bar squared c2 is equal to 0. So this is a standard second order differential equation in time. And as you know, we make this ansatz. We put the c2 equal to an ansatz. Yeah. We say that c2 be of some coefficient, what do you call it, a, into the alpha t. So alpha can be complex here. And then if you plug that in to the differential equation, then you get a quadratic equation in alpha. Plus each bar squared equal to 0, which of course gives you the solution. So then the solution becomes alpha 1, 2, let's say, is equal to minus 1, 2, omega minus omega 0, and then plus minus square root of, I call it a, nothing in the notes. So that's a is given by omega minus omega 0 squared plus 4 gamma upon h squared. So this is the general solutions. So we have linear combinations because of the alpha 1 and alpha 2. So we get t plus some coefficient b times alpha 2 t. So this is the general solution. Second order, so there are two independent solutions characterized by alpha 1 and alpha 2 and coefficients AB. So now we have to determine these coefficients A and B from the boundary condition. So let me continue. So we have the boundary condition. The initial condition is that at t equal to 0, we are in the ground state. So we are assuming that the initial system is in the ground state. So that means that C2 is equal to 0 and C1 0 is equal to 1 then, because we only have two states. So this implies then that A must be equal to minus B. So that gives us the relationship between A and B. And then we can also use the equation that C2, that this is equal to, well, let me write this down. CB plus A, and then we bring down the exponential. T, but we also know that from the differential equation we wrote in the beginning, that is equal to gamma times e to the I, and then it's minus omega 0 t times C1, like that. So then that for t equal to 0, then it gives me the solution for A, which is equal to gamma divided by IH bar alpha 1 minus alpha 2. So then that gives us the specific solution to this problem. So if we use it and the expression for C2, then we find that this is equal to gamma divided by h bar alpha 1 minus alpha 2. So that's this coefficient here. And then we have e to the alpha t minus, because b is equal to minus a. So you want to know the probability of finding the state in the second level, the excited state. So that is e to t squared. Then we find that after some algebra, simple algebra, we get this result here, divided by a. So that's the coefficient I defined earlier, and then sine squared. Squared a upon 2 times t, like this. So this is the exact solution to the problem. So one of the very few problems that can be solved exactly, and yet it is has quite a lot of relevance for real physical problems. Yeah. So it's nice. It's a nice problem that it's good to know this solution here. So one of the characteristic feature of this solution is that notice that the a here should have kept that. It's given by squared plus 4 gamma squared, like this. So we see that when omega is equal to omega 0, then a will be the smallest, because we cannot do anything about this. So this will be 0. So then a becomes small, or smallest, minimum. Then the value of C2 squared will be a maximum if sine squared is equal to 1. And we have what's called the resonance. So we get the resonance here. So this is characteristic of physical systems, that if your natural frequency, if you perturb the system in such a way that the frequency of the perturbing field is equal to the natural frequency of the system, then you get a resonance. So in this case, the natural frequency, I would say, is the separation between the two states. So that's the omega 0. So the omega 0 is just this energy difference here, so h bar omega 0. Right? So when the perturbing field is equal to that frequency, then you get resonance, kind of physically intuitive. Now, in the exercise, one of the exercise problems, I think you are also asked to do this problem, same problem, but using perturbation theory, time-dependent perturbation theory. And there you will find that perturbation theory has problems when it reaches resonance, because in the perturbation theory, you don't have this factor here, the denominator, so it blows up. And it's a coefficient. Yes, I think we will do that in the exercise problems. Okay, so this is a two-level problem. So now I want to continue with time-dependent perturbation theory. So now we do approximate methods. Time-dependent perturbation theory. So we do this exactly first by making an expansion in the potential, perturbing potential, to infinite order. So in principle, it's exact. But of course, when we apply it to a particular problem, we have to be content with a lower order perturbation theory, like first order or second order. So first order is usually what we have, and second order is already quite complicated, not to mention the third and higher orders. So let's start this by again introducing the time evolution operator in the interaction picture. So we want to develop perturbation expansion of the time development operator. So we have state in the interaction picture, time t, and we define this. It's a definition of the time development operator with the label I from t to t0. So it's just like what we have before, except that everything is now in the interaction picture. So we know from the time development operator that we have not from the time development operator, but I mean from the equation of motion or the Schrödinger equation of this state, that is just equal to t sine t, like that. So now if we use this definition here, then it follows that we have a differential equation or time development, not time development, but the differential is called time dependent equation for the time development operator. Let's do this step by step. That, but the state at t0 is an arbitrary state, so that implies that we can just drop this, and then we get time-dependent equation for the time development operator. Yes, this is our starting point, and we solve this by iteration. So now we integrate. So this should be, yeah, dt. Okay, so let me call this one here. So let me write it down like this. T1, call it T1 instead of T. That's all right, it's just a variable. T1 like that. T0. So now we integrate. So we integrate here from time t0 to time t. We do this both sides, of course. Well, the left-hand side is just a first order differential, so that gives me immediately solution. And t0 minus 0 t0. Okay. So on the right hand side is integral. These steps mistaken. T0 to t of dt1 of this quantity on the right hand side, which I cannot do anything about because I do not know what the potential are. That's an arbitrary potential. But that's the whole point of this. So we want to develop perturbation expansion. So this thing is just one because it's t0 t0 doesn't do anything. So that's just one. So then we get an iterative integral equations for the this time development operator. So let me, it's a new page here. So we have u I t0. So now I put the one on the right hand side. integral t0 t dt1 0. So that's just the same equation as before. I just put the 1 on the right hand side. So now we can iterate to develop perturbation expansions in the potential. So what we do is we replace this thing here. So this should be T1 here. Yes, so this should be T1 here. So we replace this this thing here with the whole thing. Yes, so we replace this with UI according to what we have. It's sorry, made a mistake. So we replace that thing with what we have here. So that is equal to 1 minus upon each bar integral from T0 to T1 now of dt2 vi t2. So T1 and T2 are just dummy variables. T2, T0, like that. So let's already done the whole thing. So that's become 1, and then minus I upon h bar okay, what am I doing here? Okay, so that's from the first term here. So I'm replacing this thing here with this quantity here. So that times 1. So that gives me this term here. And then I have the second order term, which is plus I h bar squared. And then I will have integral from t0 to t, dt1. And I have vi t1. And then I have this other integral from t0 to t1 dt2. Okay. So when we iterate, we're going to replace this one here with the same thing, with this one, with the general expression. So the first term will be just 1. So that will give me then the second order term here, and then plus higher order terms. Yes. So I hope you can see the structure of this equation. Yes. So you generate it when you generate the powers of the potentials when you iterate. So this has been written down up to second order. And of course, if you continue, you get third order, fourth order, and so on. Okay. So this is called the Dyson series. It's called the Dyson series. I think it was Freeman Dyson that first wrote this down. So there is a nice way of writing this time development operator using what is called the time ordering operator. It's not really an operator, but we can call it operator. It's not operator in the sense that it is not observable. So what we do is we look at the second order. So we have VIT1 like this. then we have T2 here, and then we want T2 like that. So we can write it as an integral from T0 to T for both variables, T1 and T2. So I should, yeah. But then we have to introduce this Heaviside function. Yes. T1 minus T2. So that ensures that the T1 must always be smaller than T2 must always be smaller than T1. Yes, so that will then restrict this integral to T0 to T1. So it's the same thing. But then we notice that T1 and T2 are just dummy variables. So I can interchange. Yeah. So this is equal to tt2 tt1 t1 theta t2 minus t1. I'm just interchange t1 and t2 because they are just dummy variables. So they are the same. So we can write then this original second order term as actually should be t1 t1, you see, so that's dt2 like that. So that is then just I can take both of this term, sum them up and divide by 2. They are the same. Yes. So that gives me 1/2 of integral from t0 to t dt1 integral from t0 to t t2. Now I introduce what is called the time ordering operator. So let's just call it t. But I don't want to put a hat because it's not really an operator in the sense that it corresponds to some observables. It's just definition really. So let me explain what this T means. Okay, so I have to erase this. So this operator, this time ordering operator, time ordering operator is defined in the following way. So I have two operators acting at one time T1 and T2. So this is defined to be V1, T1, V1, V1, T2, 2, and then I have plus Vi2, 2. So this operator T orders the time. Yes. So earlier time is put to the right and later time put to the left. Yes. So for example, if you look at the first term here, T2 is earlier than T1 because this has to be positive. So this has to be greater than 0. So the later time is put on the left and the earlier time on the right. So you order chronologically the operator. And the same here for the second term. So now we see that for the higher order terms, we can do some similar things. So if we have, let's say, we have the third order terms, so there will be 3 times. So there will be V, T1, and then T2, and T3. So that the third order terms. Well, there are in general, there will be n factorial ways of permuting the ordering of the time. So in this case, when n equal to 3, then there will be 3 factorial, so that's 6. There will be 6 ways of ordering the T1, T2, T3. So we can have T1, T2, T3, and then we have T2, T1, T3, and so on. So we do the permutations. So there are n factorial in general. So then this time development operator can be written as a sum over the terms from 0 to infinity of minus 5.8 to the power of n divided by n factorial. So that n factorial is to take into account that there are n factorial ways of permuting the time variables. Yeah. That becomes t0 to t. So the integral now always from t0 to t. So that's nice. T1 dot t0 t dtn. Yeah. So time ordering vi t1 vi tn like this. So we have this perturbation expansions in powers of the potential. So we notice that these are just an exponential. So we can write this in this way, in a compact way. So call it tau now. That's just a dummy variable. You can call it T1 or whatever you like. So that is a simple compact expression, the time development operator in the interaction picture. So it's easy to remember. It's just like a time development operator, but you have an integral, and then you have this time ordering. So the time ordering is very important because these operators do not commute at different times. So that's important to realize that in general, this thing do not commute different times. Not equal to 0. So that's why we need the time ordering. Because if they commute, then of course we do not need to worry about the time ordering. Yeah. If we use the Schrödinger picture, this thing I should also comment here. So we have this exactly the same differential equation. So we have in the Schrödinger picture, we have this. It's equal to h, which can depend on the time also. So it can depend on time. So this is the Schrödinger picture. So we can also write the time development operator in the Schrödinger picture in exactly the same way, because there is no difference between what we have done here for the interaction picture and this one here. It's exactly the same differential equation. So the solution is exactly the same form. So we can write the solution for the time development operator and the Schrödinger picture in the same way, except that we have h instead of v. So we have this. These are the formal solution to the Schrödinger equation. So you can see that if you compare these two, although they are identical, they are equivalent at least, this one is much more useful for making a perturbation expansion because you only have the VI in the exponential. But this guy here, H contains H0 plus VT. So that's a complicated object, especially that this H0 and the VT, they do not in general commute. So this is a rather complicated expression. It looks simple, but it's not so useful in the sense that you cannot easily apply this form in practice. So this is the general solution. So time development operator in terms of the potentials V. So if I have time here, okay, we can continue a little bit. Just there are 4 or 5 minutes. I would like to consider now a general problem with harmonic perturbations. So maybe I can just describe the problem. So this is a more general harmonic perturbation problem. So this is an example of application of the time-dependent perturbation theory. So we did it before for the two particle, not two particle, but two level states. But now we want to do this in general. And obviously we cannot solve this analytically anymore because now we have many states. So we have to use some approximate method, and that's where the time-dependent perturbation theory comes in. So the form of the potential, perturbing potential, is this way. We have the usual harmonic, exponential, and then we have a dagger. Okay, so this is obviously Hermitian. It has to be, because we are talking about some physical problems. So our potential must be Hermitian. So we assume that the initial state is one of the eigenstates of H0. So call it I like this. So that's energy I. So that's the unperturbed. So you can imagine that the system is, let's say, in the ground state, and then you apply this time-dependent field. So you want to know what's the probability of finding the states in the higher energy states. So you have kind of transitions in the initial state, so in the ground state, to the higher excited states. So these are the typical problems in physics that you want to study. So if you do photoemission experiment, like what they are doing in the Max 4, you have a material and you shine lights on it. So the material is in the ground state, and you look at the system, or maybe you should do optical experiment instead. It's easier to relate it to this problem here. So you shine light, and then you look at the outgoing photons, and measure the energy. So by measuring the energy, then you know how much of the energy is absorbed by the system by looking at the absorption curve. So to analyze this problem, you need to know how the initial state is coupled to all these excited states. And this perturbation here will be the electromagnetic field of the photons. That's the perturbing field. Okay, so I don't think we have time here to go through the derivation, so we have to do this next time. So that's okay. So I think this week there is no class because it's a holiday. I think it is Christy Himmel's Fair today, Thursday, and then we don't have a class on Friday. Slam dunk. So yeah, I think we start again next week on Tuesday. Okay, so let's see if there are any questions before we quit. Okay, very good. You can always ask questions if you have some questions. Later, you can just send me emails or something. Okay. Very good. Yes. Someone asks questions. Okay. Goodbye then.
Thanks.
Bye.
Bye.
Thank you.
Bye.
Bye bye.